This video is about the design of solar PV system for a home. The home consists of the following appliances: 3 numbers of fan and 4 tube lights, 1 television set and 1 laptop. Each of this fan has a capacity of 75 watts. The tube light is of 40 watts and TV is of 40 watts and laptop is of 60 watts. So this is the power capacity of individual appliances. So this three fans are running for a duration of 8 hours, and tube light, 4 tube lights run for 4 hours, and this is the duration for which the TV is switched on, 2 hours, and for 2 hours the laptop is switched on. Now the total power consumption: 225 watts. So this is the total power. So you have to multiply the total number of fan and the power of a single fan. So 3 numbers of fan into 75 watts. So we'll be having 225 watts. Next, 4 tube lights are there. The power capacity of each fan is 40 watts. So total you'll be having 160 watts. Similarly, 1 into 40, 40 watts, and 1 into 60, 60 watts. Now energy consumption. For energy consumption, you have to multiply the power and time duration. So 225 watts into 8 hours will be getting 1800, and 160 watts into 4 hours will be getting 640. Similarly, you can get for this TV and for laptop. Now the total power is 485 watts. You have to add this 4 values: 225 watts, 160 watts, 40 watts and 60 watts. Next, the energy consumption in watt hours. You have to add this 4 values: 1800 plus 640 plus 80 plus 120. So we'll be getting 2640 watt hours. So WH, watt hour. So this is the load which you have to run. The total wattage is 485 watt and the energy consumption is 2640 watt hour. To run the load using a solar PV, you will be requiring batteries and inverter. Here I have considered the inverter efficiency as 93% and the battery efficiency as 95%. This side will be running on AC and this portion will be running on DC. The DC voltage can be of 12, 24 or 48 volt. So what happens if you change the voltage? This complete circuit depends upon the chosen voltage. See, if I choose 24 volt, here I have chosen 24 volt. So what happens if the voltage is lower and the voltage is higher? If the voltage is higher, in this case, if the voltage is higher, the current will be low, and if the voltage is lower, the current will be high. If the current is high, the losses will be more, that is the I square or losses will be more. So we have to minimize this I square or losses. How you can do this? By going for a higher voltage. So this is a high voltage and this is a lower voltage. Lower voltage in the sense I am telling 12, 24, and high voltage in the sense means here the 48. So if I choose 48 volt, the current will be lower and the I square R losses will be lower. And if the voltage is lower, the current will be higher and the I square R losses will be more. We have to minimize this category, low voltage and high current. Now first we shall design the inverter. So this is the inverter in output, and this is the inverter input. The efficiency is 93%. You know what is the inverter output. So this energy has to be fed to the load. So this is calculated. It comes around 2640 watt hour. You know what is the efficiency. From this you can calculate what is the input to the inverter. So efficiency of the inverter is given by the energy output from the inverter to the energy input to the inverter. So E1 I know what is E1 2640 watt hour. Efficiency I have assumed to be 0.93. In percentage you can say it as 93%. From this calculate E2. E2 comes around 2839 watt hour. The inverter efficiency can be written as a total wattage divided by inverter input. Inverter input is equal to total wattage divided by inverter efficiency. The total wattage you have calculated, it comes around 485 watts. Efficiency I have assumed 0.93. On solving this, we'll be getting 522 VA. So up to this, we have calculated what is the inverter output, that is the energy consumed by the load, and the inverter energy consumption, that is the energy input to the inverter, that is 2839 watt hour, and the inverter VA, this is 522 VA. Next we have to go for the battery part. I have considered the battery efficiency to be 95%. So efficiency is given by output by input. Output is E2 and input is E3. From this calculate what is E3. You know what is E2 and the battery efficiency. So E3 comes around 2989 watt hour. So this is the input to the battery, or you can say it is the solar PV output energy. For the battery, you have to consider the following two terms. One is the depth of discharge and the next is the days of autonomy. Assume you are having a 100% charge. So at 100% charge means you are having a 100% state of charge. So nothing has been discharged. So the depth of discharge is 0% at this point. Now your battery charge is 70%. So 70% means 30% has been discharged. So 30% has been discharged and the state of charge is 70%. So state of charge indicates how much charge is present, and the depth of discharge indicates how much charge has been discharged. Next is the days of autonomy. So days of autonomy is taken into account while considering the rainy days or cloudy days. In this problem, I have considered the days of autonomy to be 2. So this is the inverter, battery and solar photovoltaic. This part I have calculated and this also has been calculated. So I have assumed the depth of discharge to be 50% and the days of autonomy to be 2. Now the actual battery capacity has to be calculated. The actual battery capacity is equal to what is the input to the battery. So the input to the battery has been already calculated. It comes around 2839. Sorry, the input to the battery is 2989 watt hour. So E3 2989 watt hour, and X is the days of autonomy. In this problem I have considered the DC voltage to be 24. So 24 volt, and depth of discharge 50% or 0.5. 50% depth of discharge means the load can use the charge from the battery till the 50% charge has been out. So if you are having 100% charge, your battery will be discharging till it comes 50%. After this you have to once again charge the battery. It can't go below 50%. So that is called as 50% depth of discharge. It is a value which shows the point up to which you can discharge your battery. So actual battery capacity is equal to battery input energy into days of autonomy into DC voltage into depth of discharge. So this on solving you will be getting 500 ampere hours. Next is the number of sunshine hours. It can vary between 4 to 5 hours. Now you have to find the module wattage. So how you can calculate the module wattage? So this is the battery input. The battery input divided by the number of sunshine hours. So E3 is 2989 watt hour divided by 4. You will be getting approximately 750 watts. Once again I have drawn the layout. So this is the load, inverter, battery, PV panel. So the load consumes 2640 watt hour of energy, and the input to the inverter is 2839 watt hour, and the input to the battery is 2989 watt hour. This is the wattage, 750 watts. This 750 watts you can't get in the market. So what you can do to get the 750 watts, either you can choose 15 numbers of 50 watt panel or 8 numbers of 100 watts panel or 3 numbers of 250 panel. So if the 50 watt panel is suppose X rupees, so the total cost of this is 15 into X. If the cost of 100 watts panel is Y, then the cost for procuring 8 numbers of 100 watts panel is 8Y. Similarly you can do for 250 watts. Suppose this is if your 250 watts panel is Z rupees, then you have to buy 3 numbers of panel each of Z rupees. So among this you have to choose which is giving a lower value. So this is how you will be designing a solar PV system, and how you are finding the number of panels required. Thank you.